Hello and welcome to this presentation for the paper Context Embedding for Sequential Service Recommendation. My name is Benjamin Amankwata, and this paper was co-authored by myself and Dr. Kenneth Fletcher, who is my advisor and the director of the Services Computing Lab here at UMass Boston. We'll first go over a brief outline of the talk. First, we'll talk about our motivations for this work. Second, we'll highlight the specific contributions that this work made. And then we'll take an in-depth look at our model. We will discuss higher order latent interactional context, HOLIC or HOLIC for short, which is our novel formulation of interactional context, a major contribution of this work. We will talk about deep embedding clustering and how we use that to formulate HOLIC. And then we'll also talk about the neural attention component of this model. We'll then discuss our experiments and results, and we'll conclude with possible future extensions to this work. So let's get right in. So beginning with motivations, in the field of contextual sequential recommendations, traditionally context labels have to be predefined or handcrafted. And this requires additional effort to augment the training data set in addition to actually coming out with these labels. The second is that the context attributes may not be available for each data point, resulting in data sparsity and dimensionality expansion problems. And finally, handcrafted or predefined context attributes may not reflect the optimal dynamics for the service recommendation process. Now we'll briefly discuss the contributions of this work. Inspired by a concept called hyperspace analog to context, or HAC, we propose high order latent interactional context, HOLIC, a novel formulation of interactional context. We propose a novel model that leverages HOLIC and neural attention for improved sequential service recommendation. Now, to the best of our knowledge, this is the first work to unify interactional and representational context in a single model for sequential recommendation. Finally, we perform experiments to evaluate and validate our proposed model using 4 real-world online service data sets. So, a brief overview of the model. Our model roughly has 3 main components. The first component is a classic encoder-decoder framework, which is what you would see down the middle of this diagram. And in this model, the encoder-decoder framework is composed of 2 GRU, gated recurrent neural network modules. At the top of this module is fitted a neural attention mechanism to help focus the learned representation on specific parts of the input sequence. And at the bottom of the diagram is the deep embedded clustering component. Overall, this model is trained in a multitask training approach that minimizes a weighted linear combination of the cross entropy loss from the decoder and a cluster assignment loss from the KL divergence derived from the deep embedded clustering model. And we will shed more light on this as the talk progresses. So we begin with hyperspace analog to context. This is a model formulation of context in which context is formulated as a multi-dimensional space in which moving across that space is equivalent to continuously changing information from various context sources. So in essence, HAC is an n-dimensional space where each dimension describes a data type and a value set for a specific type of context. And Perhaps one of the novelties of this approach is that the dimensions in HAC are heterogeneous, which is that values can be of different types. Example, you can have both categorical, discrete, and continuous variables at different dimensions in HAC. Our model is inspired by HAC, which offers a valuable framework for thinking about modeling latent context, where the context types may not be interpretable and the structure not well understood beforehand. So based on that, we formulate HOLIC, which is an acronym for Higher Order Latent Interactional Context. And the formulation of HOLIC is as follows. Given an input sequence and no additional context information, we first seek to learn a k-dimensional context vector, which will denote C, such that each index of this vector represents the relative contribution of a set of discrete context sources. Our methodology is as follows. First, we map the input sequence into a d-dimensional latent space. Then we learn a set of cluster centroids in that latent space. And then we determine the proximity of each input sequence to the respective cluster centroids. We call C a higher order latent interactional context. Now, we argue in this work that for sequences which are contextually dependent, we expect that representations in latent space will cluster around significant context sources. And in that vein, C is analogous to a point in HAC. So next we'll talk about deep embedded clustering and how we use that to formulate HOLIC. Now the objective of deep embedded clustering is first to learn a suitable representation of the input sequence using a deep learning framework, and then subsequently to apply a clustering technique to the learned input representation. Classically, this is done in two stages. In the first stage, we learn a nonlinear transformation from the input space to the latent space, which we do with a deep neural network. And in our work, this will be equivalent to the final hidden state of the GRU encoder network. Now, next, we learn a set of k-centroids in the latent space. In this work, we use the student's t-distribution as a kernel to measure the similarity between an embedded input sequence and a respective centroid. So formally, we define an L-dimensional vector, Zi, for the input representation latent space. We also denote a set of k L-dimensional vectors to represent each of the k centroids in latent space. As we just mentioned, we use the student's t-distribution as a kernel to measure the similarity between the input representation and each of the k centroids. Now we denote this distribution as Q. Now the resultant formulation of a point in this distribution Qij is the normalized similarities between the input sequence and each of the respective cluster centroids. Now, in the absence of a ground truth distribution to help us learn Q, we formulate an auxiliary target distribution P. Now, P is derived by squaring and normalizing each point in the original distribution. The squaring has the effect of putting more emphasis on points assigned with high confidence. That is, we try to shift the probabilities closer to 0 or 1. And normalizing prevents large clusters from distorting the latent space. We calculate the cluster assignment loss as the KL divergence between the original distribution Q and the auxiliary target distribution P. And learning Q is a matter of minimizing the scale divergence. Now, we model the decoder conditional probability as the probability of the next item in the input sequence given one, the set of hidden states from each time step in the GRU encoder, and the final hidden state of the GRU encoder. We calculate a weighted alignment score for all hidden states, where the alignment score is a normalized similarity measure between the final hidden state of the encoder and each of the hidden states at each time step. The decoder then takes as input the weighted alignment score, the final hidden representation of the encoder, and then predicts the next item. As we mentioned earlier, the entire model is trained using a multitask training approach that minimizes a weighted linear combination of the cross entropy loss from the decoder prediction and the cluster assignment loss. So we'll now briefly describe our experiments beginning with the data sets. So in this work, we use 4 public data sets, and we've provided the metadata for those data sets here. So very briefly, we use Yelp, which is a subset of Yelp's business reviews and user data across 8 metropolitan areas in the US and Canada. We use the Movie Lens 25 million data set, which is a user movie interaction activity from the Movie Lens recommendation service. We also use the Foursquare data set, which is global check-in data from Foursquare that contains check-in from users in cities across 77 countries. And finally, the Last FM 1000 dataset, which is the whole listening habits for nearly 1,000 users on the Last FM platform. Now we'll discuss important hyperparameters in this work. So among the significant hyperparameters, first of all, is the number of cluster centroids, which we denote as K, which in this work we found to be different across data sets. And then we have gamma, or the scaling factor for the KL divergence loss for the multitask training loss. And then alpha, which is the degree of freedom of the student's T distribution. Table 4 just shows the optimal cluster centroids across data sets. And for simplicity, we just chose data sets in multiples of 250. Now we'll briefly discuss our results. So we compared our model to 3 other models across 2 metrics, MRR, and then recall. And so the baselines choosing are the standard transformer and a standard RNN network, which is a GRU network. And then we have a GRU network that is also fitted with an attention mechanism. And as can be seen, our model outperforms all of these models on all the data sets, which proves its efficacy. So in conclusion, in this work, we have proposed HOLIC, which is a higher order latent interactional context, a novel formulation of interactional context for context-aware sequential recommendation. And we have proposed also a sequential service recommendation method that leverages HOLIC, a presentational context and neural attention mechanism for improved sequential recommendation. We've compared our models to other approaches, both recurrent neural network and transformer architectures on 4 benchmark datasets, and we've demonstrated the superiority of our approach to the baselines for next item recommendation. So as far as future work, we hope in the future to investigate the internal structure of interactional context with a particular focus on delineating probable hierarchical relationships between context, resources, and within the HOLIC framework. We also hope to explore analytical approaches to optimizing the number of cluster centroids in our formulation of HOLICs. And with that, thank you so much for taking the time to view this presentation.